Okay, in this problem, got a beam, okay, but it's subjected to a moment that is not just around a single axis, okay, and because of that, we need to take into account that it can have some shear stress going in both directions. So the total normal stress is the moment around the z-axis times y all over the moment of inertia about the z-axis, and then plus my times z, so that's the moment about the y-axis times z all over the moment of inertia on the y-axis. Because what basically happens here is this moment can be broken up into two moments here, right? So this would be m cosine 30, which would be about the z-axis, and then right here would have m sine 30, which would be about the y-axis. So I've got basically moments going around each axis. So what happens is, take for example the moment around the z-axis. As that guy gets bent, the top of that will be in tension, and the bottom of that will be in compression, right? Whereas about the y-axis, as I rotate around that, the left side will be in tension based on the direction that I've got going there, and the right side will be in compression. Okay, so depending on where on that cross-sectional area you're located, you'll have a different stress. So it could be a tension, a compression, could be a combination of each. But what I know for sure is that this point right here, that is the maximum tension up in the upper left, because both the top and the left side are in tension. And then down here is the maximum compression. And what we're trying to find here is oh, well, they have the allowable tension and compression, right? So I've got to find both of them. So the maximum tension occurs in the upper left, the maximum compression occurs in the lower right. And what I do is I break it up into pieces and add them together, because I've got some moment caused by a moment around the z-axis, some about the y-axis, and add them together. Okay? So, and I'm trying to find what that m would be. Okay, so I know the angle that's at, so I know the m's. I've got the sine and cosine of 30. Y and z will either be, let's see, what would that be? Oh, I guess I have to find the neutral axis. That's probably the first thing I need to find. So the y-axis is actually in the neutral axis. Okay, um, I need to find this. This is where I'm going to start. I need to find where the neutral axis is. So I'm going to find y bar, which is the centroid. So to find y bar, I've just got a big rectangle and a small square, and they're subtracted off. Okay, so the center of that big rectangle is 300. So 0.3 times the area, which will be 0.3 times 0.6, okay, minus the square, which from the bottom will be 225, times, what's that, 150 by 150, so 0.15 times 0.15, all divided by the total area, which will be 0.3 times 0.6 minus 0.15 times 0.15, right? So that's how I find essentially where the centroid, where that neutral axis is located. Calculating that, I get about 310 millimeters, or 0.31 meters up from the bottom. Okay, so that gives me where the location of the z-axis actually is, where that neutral axis is. Now, since I've got that, I'll go ahead and find the moment of inertia about the z-axis, about that neutral axis, which I need to use the parallel axis theorem. So again, it's going to be the big guy minus the little guy. So it's going to be 1/12 times 0.3 times 0.6 cubed. That's 1/12 bh cubed. Okay, but then I need to do the parallel axis, which will be the area, which will be 0.3, 0.6 times, again, the center of the big rectangle is 300. the center of the neutral axis is the 310, so I go 0.310 minus 0.3 squared. So that's the moment of inertia of the big one. And what I do is I subtract off the square, which is going to again be 1/12 bh cubed, which will be 0.15 times 0.15 cubed, plus the area, which would be 0.15 times 0.15. That's the area of that square. And then its location is 225. So I say 0.3107 minus 0.225 squared. Okay, that's the parallel axis theorem. From that, I find that the moment of inertia about the z-axis is 5.213 times 10, to the minus third, and again, that's meters to the fourth. Okay. Now, for about the y-axis, which I'm also going to need, it's a lot easier. I don't have to do parallel axis theorem because that does go through right through the center of that. So on that one, the moment of inertia about the y-axis is much more straightforward. It's a 1/12. Now, bh cubed, the b and the h flip on this one, so it's going to be 0.6 times 0.3 cubed, right? So that's the big one. And then I'm going to subtract off the square, which, again, there's no parallel. These both go right through the center, that y-axis, so I don't have to do any parallel axis theorem. But that's going to be 0.15 times 0.15 cubed. And that equals the moment of inertia about the y-axis is 1.308 times 10 to the minus 3. And again, that's meters to the fourth. Now, I should be able to plug and chug. Okay, so we'll go ahead and start with the, let's see here, we'll start with the tension. Okay, so the tension is going to be in that upper left. Okay, and the tension's allowable stress is 125 times 10 to the sixth, and that's going to equal the moment. Okay, where I'm going to start with about the z-axis, so that's going to be the cosine of the angle is the moment about the z-axis. Okay, the distance, okay, again, I'm doing that top left corner, so that's going to be 0.6 minus the location of the neutral axis, which is 0.3107, okay, all over the moment of inertia about the z-axis, which is 5.213 times 10 to the negative 3. To that, I'm going to add, going about the y-axis, where I've got the m sine 30, okay, its location is 150 from the center, right, because they just move over 150, and then take that by the moment of inertia about the y-axis, which is the 1.308 times 10 to the minus 3, okay. From this, I solve for that moment, okay. So the moment that creates that largest tensile stress of 125 megapascals gives me m equal to 1186, and that's going to be kilonewton meters. Okay, now I do the same thing for the compression. It's going to look very similar, but instead I'm going to use 150, which is the allowable compressive stress. Okay, and these are both going to be now in compression, and really the only thing that's going to change is the y value. Okay, because about the z-axis it's still m cosine 30. Okay, but here's the difference. Now I'm going down and to the right. So to go down from the neutral axis, I go down that 310.7 millimeters. Divide that by the 5.213 times 10 to the negative 3. Okay, and then the compression, okay, will look the same in that it's m sine 30 again, this is about the y-axis, okay? It's still just 150 over, it's just in the other direction. And then I is still the same in this direction, which is 1.308 times 10 to the minus third. Solving this one for m, the m required to create that much of a compressive stress is 1377. Okay, so if I want to find the allowable moment so that neither of them break, I need to use the smaller one. So this is actually the answer here. So again, when I've got bending in more than one direction, I just break it up into pieces and then add the stresses about each axis, add them together to find the total stress.